Hi everyone, in today's video we are going to continue working with radicals. We are going to do operations with radicals, and we're also going to do operations with complex numbers today. So in this video you're going to learn how to add, subtract, and multiply nth root radicals. We're going to also add, subtract, and multiply complex numbers, and then we will do a little bit of division with nth root radicals, not with complex numbers. We're going to use the quotient property, and we're also going to rationalize the denominator. So let's get started. First, if we have radicals, they have to have the same index and the same radicand in order to be considered like terms. If that's true, then we can add together their coefficients. Now the first step whenever you're given a problem like this is always going to be to take each radical individually and simplify it completely. And then after you do that, if the index and the radicand match, then you can perform the operation, either addition or subtraction, on the coefficients in front. The radicand itself is not going to change when you perform addition and subtraction. So in this first example, notice that the radical in both of these is the cube root of 2. That means, because these are like terms, that we can, in this case, add together the coefficients. So we're adding together the 5, and the coefficient in front of this term is a 1. So 5 plus 1 is 6, and then that radicand, the cube root of 2, stays the same. This is the same thing as if I did 5x plus x. I would say 5 plus 1 is 6, and that variable of x would be the same. The same thing is happening here. We just have an uglier thing in the place of that variable, that radical. All right, the second one is a little bit more challenging because we need to simplify first. The square root of 3 does not simplify, but 27 is 3 times 9, and that's a perfect number, so we need to simplify it. So I'm going to leave this 2 square roots of 3 alone, but the square root of 27 I'm going to write as 3 square roots of 3, because the square root of 9 is 3, so it comes outside. You'll notice now that I do have like terms because both of these have a square root of 3. That means then that the coefficients out front can be subtracted. 2 minus 3 is negative 1, and the radical, the square root of 3, stays the same. So my final answer is negative square root of 3. Now, we are going to follow a little bit different of a process with complex numbers when we add and subtract, but this will probably be a little bit more what you're used to with variables, because a lot of the time, imaginary numbers, the I, it acts just like a variable. There are a couple exceptions to that, but we'll get into that with multiplication later. So if the problem is a subtraction problem, we're going to distribute the negative to create addition, and then we're going to add, combining like terms, simplifying as we can. This first one is an addition problem, so I can immediately just start looking for my like terms. I have 4 plus 3 is 7, and I have negative I plus 2i, so that's 2i minus I, which is 1i, and that's a positive one. My final answer then is 7 plus I. Notice that I wrote this with the integer first and the imaginary number coming second. In the second one, number 4, this is a subtraction problem, so I'm going to distribute that negative, which changes all of the signs to be the opposite in that second term, or in that second set of parentheses. So now I've got an addition problem. I'm doing 7 minus 1 is 6. Negative 5i plus 8i is positive 3i. Notice that my integer comes first and my imaginary component comes second. All right, so now let's get into multiplication, where things get a little bit hairier. When we have radicals, we only have to have the same index in order to have like terms. The radicand can be different. So as long as, in this case, they're both square roots, we can multiply them. If one was a square root and one was a cube root, those wouldn't be considered like terms. We would not be able to multiply them to combine. So again, we are going to simplify each radical completely individually, then if the index is the same, we're going to multiply the coefficients, and we're going to put the radicands under one radical, and then we're going to simplify that radical completely. All right, so let's do some individual work. If I have negative 12 as my first radicand, 12 is 3 times 4, and that's a perfect number, so I'm going to rewrite this first one as 2 times, because that 2 is the coefficient out front, the square root of 4 is 2, and then I've got that square root of 3 still inside. So I've just simplified this one. Now there is a negative. I almost forgot about it. So I'm going to erase my square root of 3 because that I comes out of that radical as well. The second one over here, I have 18, and 18, let's see, how do we want to do that? Maybe 2 times 9, because 9 is a perfect square. So I'm going to put my multiplication sign, and then I'm going to say 5 times, because again, that's that coefficient out front, 5 times 3i square roots of 2, because the square root of 9 is 3, the square root of a negative is I, and then the 2 stays inside of the radical. Okay, so let's just simplify. If I look at this first term here, I've got 2 times 2i, so that's 4i square roots of 3. And then in the second one, I've got 5 times 3i, so that's 15i square roots of 2. All right, so we have simplified each one individually. We do have like terms with this one because both of these are square roots. So now we're going to multiply together our radicals and our coefficients. So I'm doing 4 times 15, which is 60. I times I is I squared. We'll come back to that in a second. And then the radical, I'm going to put the 3 and the 2, both radicands, inside. That's going to be 6. It's not going to simplify it at all. Sometimes it will, but this is the easier one, so that's not the case. So it looks like we're almost done. 60i squared times the square root of 6. But there is a new idea that I want to introduce here. When we defined I as the square root of negative 1. What happens if I square I? So now I take this square root of negative 1 and that whole quantity gets squared. Remember, squares and square roots undo one another. So that means I squared is equal to, I squared is equal to negative 1. This means that I need to do this simplifying anytime I get an I squared in my work. We're going to do a substitution. Every time you see I squared, you're going to rewrite it in your next step as negative 1. So that means we have 60 times I squared gets substituted as negative 1 times the square root of 6. So our final answer is negative 60 square roots of 6. That's my final answer there. All right, so now let's do a little bit more with complex numbers, with those imaginary i's. When we're doing operations like multiplication with complex numbers, we're going to apply the distributive property. We're going to combine like terms just like we would with any variable, but we do have to remember that I squared is equal to negative 1 because the square root of negative 1, if I square it, is negative 1. So this is going to be super, super important. We can't forget about it. All right, so let's go. The first one says 2i times 9i. This one doesn't have any distributing per se because it's just two terms. So I'm going to do 2 times 9 is 18, and I times I is I squared. I have an I squared, so I'm going to rewrite that as a negative 1. My final answer is negative 18. The second one, I do need to do some distributing. I have 5i times negative 2 plus I. So I'm going to distribute 5i times negative 2 is negative 10i. And then I'm going to distribute 5i times I is positive 5i squared. Okay, so I have an I squared, which means I'm going to rewrite that as a negative 1. and I get negative 10I minus 5. And to put this in our standard form, I'm going to switch it around. I'm going to put the integer first and then the imaginary part, because that's how all of our complex numbers will always be formatted. The integer goes first, the plus or minus sign, the coefficient if there is one, and then the imaginary number at the end. All complex numbers. Okay, so this last one has two binomials, 8 plus I and 3 minus I. So I'm going to be distributing on this one a lot. So here we go. 8 times 3 is 24. 8 times negative I is negative 8I. Then I'm going to distribute the second term. I times 3 is positive 3I. I times negative I is negative I squared. Okay, so I have some terms to combine here in the middle, and I'm also going to do some substituting for that I squared very carefully. So 24 minus 5I minus, and then it's the I squared part that gets turned into a negative 1. So that negative is going to be a positive. I do have like terms here. You've got 24 minus 5I plus 1. I have integers here, or whole numbers, so I'm going to add those together, and my final answer is 25 minus 5I. All right, so let's keep going. Division is the last thing that we need to talk about, and there's a lot to do with division. So we're going to talk about division in two ways. The first is the quotient property of radicals says if you have a quotient underneath a radical, so you have a square root of a quotient, that's the same thing as the square root of the numerator divided by the square root of the denominator. So we can go back and forth with these two things. If the two numbers, the numerator and the denominator, are divisible, then it's going to make our life really easy. So if I gave you a problem like number 9, the square root of 20 divided by the square root of 5, when I see that and see the 20 and the 5 both with square roots, because again, we have to have the same index to get like terms, just like with multiplication, I know that I can combine these to be the square root of 20 divided by 5. And that makes my life easy because I can do 20 divided by 5. 20 divided by 5 is 4. So then I have something without a fraction to deal with, which is always nice. The square root of 4 simplifies to 2. All right, let's try a couple more that get a little bit more complicated now. Now, a lot of times it's going to work out that when we are simplifying with a radical, we're not going to have a radical on top and bottom, or maybe we will, but they're not going to be divisible with one another. And so we can't use that quotient rule. So there's this other strategy called rationalizing the denominator. And we're going to use this term a lot. So I want you to put a star by it on your paper. Rationalizing the denominator is something that you are going to get really comfortable with over the next couple of classes. All it means is get the radical out of the denominator. You are not allowed to have a radical in your denominator if it's fully simplified. Your final answer can have radicals up top in the numerator, but not down in the denominator. So our steps are going to be, first, we're going to simplify the radical in the denominator if we can, and then we're going to multiply both the numerator and the denominator by something that makes a perfect square in the bottom, and then simplify it. So let's look at what that means. Number 10 says 5 divided by the square root of 3. The square root of 3 doesn't simplify at all, so I'm ready to go on to the second step where I multiply. So I'm going to rewrite my 5 divided by the square root of 3, and then I want to multiply by a square root on top and bottom that gives me a perfect number in the bottom. So because there's a 3 there, what I really want to do is square root of 3 times square root of 3, because 3 times 3 is 9, and that is going to simplify in my next step to just 3. And that doesn't have our radical in the denominator anymore. That's good. That's what rationalizing the denominator means. So let's multiply on the top by the same thing, the square root of 3. So up top I have 5 times the square root of 3. That's going to stay as it is. There's nothing I can do to combine those two since one's inside of a radical and one's not. And then my numbers on the outside, 5 divided by 3, that fraction doesn't simplify at all, so that's my final answer. Now, sometimes the number that's in the radical, the radicand, is going to be something that simplifies. So you might have a step in, like you do in number 11, where you have to do something before you multiply on top and bottom to get rid of the radical. In this one, we have the square root of 8, and I know that 8 is 4 times 2, and I can take the square root of 4. So before I do any rationalizing of the denominator, I'm going to simplify that radical completely. So that gives me 1 over 2 square roots of 2. Now, this coefficient of 2 here, he's totally fine in the denominator. He's not inside of a radical, so I'm not going to stress about him. It's the square root of 2 that I need to deal with. So I'm going to multiply on top and bottom by a square root, and I'm going to multiply by the square root of 2, because the square root of 2 times the square root of 2 will give me the square root of 4, and that simplifies. So I'm trying to force this denominator, the radical, to have a radicand that's a perfect number. This 2 that's out in the front, he's just going to come along for the ride when I do this multiplication. Notice that I didn't multiply by that coefficient of 2 in my rationalizing part, where I chose what to multiply by on top and bottom. Okay, so because we did it in the bottom, we're going to do it on the top. That's 1 times the square root of 2, which is just the square root of 2. And then my denominator, I'm going to simplify more. The square root of 4 is 2, so that's 2 times 2 in the denominator, which means I have the square root of 2 all over 4. The 2 is inside of a radical, the 4 is outside of a radical, so I cannot do anything else. That problem is done. I don't have a radical in my denominator anymore, and nothing simplifies any further. All right, so that's the basics with square roots, but what about when we have an nth roots, like a cube root or a fourth root? We're going to do a similar kind of process, but we're going to have to be a little bit careful about what number we choose to multiply on top and bottom by, because we want to get a perfect number inside. That's, in number 12's case, a cube. So we have a cube root of 2 in the denominator for number 12. So when I do this cube root and I choose to multiply by a cube root on top and bottom, I want to think about what cubes, what perfect numbers do I know that have a 2 in them? And I immediately think of 2 to the 3rd power is 8. So I want to get a 8 inside of this radical. So I need to do 2 times what is equal to 8. And that's 4, so that's what I'm going to multiply on top and bottom, because that gives me 2 times 4 inside my radical, which is an 8. In my next step, I'm going to take the cube root of 8, it's going to be a 2, and then I don't have a radical anymore, which, remember, that's my goal. All right, so we've done the bottom, let's do the top. We have 7 times the cube root of 4. That doesn't simplify at all, so that keeps my work nice and easy, and I'm done there. Let's look at one more of these. The cube root of 4 doesn't simplify at all, so let's try to get a perfect cube down in that denominator. I need to multiply by a cube root, and it needs to be a perfect number here. So I'm looking for a cube root of something. 4, you know what, I'm going to go with 8 again, because 8 I can take the cube root of. So to get to 8, I'm doing 4 times 2 to get 8, which means I've got that 2 on the top and bottom in the thing that I'm multiplying into it. All right, so up top I've got 5 times the cube root of 2, and then my denominator simplifies. The cube root of 8 is 2. My denominator is just along, or my numerator is just along for the ride right now. And that's not going to simplify because I can't divide 5 by 2 and make it any more simple. So that one is done. All right, so I know that's a lot. There's one more situation that I need to show you, and that is, what do you do if you have two terms in the denominator? You'll notice that for all four of these, there was just one radical. But if you look at these last two, notice that 14 says 3 minus the square root of 7. So now I don't just have a square root, I have subtraction happening. Whenever that happens, we're going to be multiplying by what's called the conjugate. And this is another big vocab word that I want you to get comfortable with. So please put a star by that on your paper. It's just a fancy word that means the same thing but with the opposite sign on it. So if I'm looking at 14's denominator, 3 minus the square root of 7, the conjugate of that would be 3 plus the square root of 7. The sign is changing on the part that has the radical. Notice that the integer part stays the same. It was only the sign on the radical that changed. So let's look at why that's helpful to us. If we have 2 over 3 minus the square root of 7, and I'm going to put that in parentheses because I'm about to do some distributing, and I multiply it on top and bottom by the conjugate, 3 plus the square root of 7. Let's just look at our denominator for a moment. 3 times 3 is 9 when I distribute. 3 times square root of 7 is positive 3 square roots of 7. When I do negative square root of 7 times 3, I get minus 3 square roots of 7. And then when I do my last, negative square root of 7 times square root of 7 is negative square root of 49. Now I know that looks rough, but notice a couple of things here. 3 square roots of 7 minus 3 square roots of 7, those cancel out. 3 minus 3 is 0. And the square root of 49, that's something that's easy to take the square root of. That's 9 minus the square root of 49 is 7. And that's always going to happen. Your middle two terms are going to cancel out when you use the conjugate, and the last term is going to be a perfect number that gets rid of the radical, which remember is why we're doing all of this division. We can't have a radical in our denominator. So let's do our top then and finish this one up. Up top I have 2 times 3 is 6, and 2 times the square root of 7. So that's plus 2 square roots of 7. These two can't combine because they don't both have radicals in them. This would need a square root of 7 in order to combine. So 6 plus 2 square roots of 7 is as far as that one goes. All right, so let's finish that up. I've got 6 plus 2 square roots of 7 up top. 9 minus 7 is 2. Now I do have some fraction simplifying that I need to do here. If I split up this common denominator into two denominators, so the 6 goes over the denominator of 2, and the 2 square roots of 7 goes over the denominator of 2. You'll notice that you can do 6 divided by 2. That's 3. You can also do 2 divided by 2. That's 1. So my final answer then is 3 plus the square root of 7. Let's do one more of those because I know that that's a hard problem and all of this division is kind of a lot to think about. So first let's think about what the conjugate is. If I have in my denominator 1 plus 2 square roots of 6, the conjugate would be 1 minus 2 square roots of 6. So that's what I'm going to multiply by on top and on bottom. Sorry, my power cord came out and my battery's not happy. All right, there we go. All right, so I'm going to multiply by 1 minus 2 square roots of 6 on top and bottom. I'm going to use parentheses. I'm going to add parentheses over here so I don't get lost. And now I'm going to do a bunch of distributing. The good news is the top is 1 times that quantity, so that's just 1 minus 2 square roots of 6. The denominator is where I'm going to have to do a ton of distributing. So let's go for it. 1 times 1 is 1, 1 times negative 2 square roots of 6 is negative 2 square roots of 6. 2 square roots of 6 times 1 is positive 2 square roots of 6. And my last, 2 square roots of 6 times negative 2 square roots of 6. So that's 2 times 2. That's a negative 4. And then square root of 6 times square root of 6 is 36 inside. So now let's do our simplifying. Our middle two terms, notice they divide or cancel out. Negative 2 plus 2 is 0. Then I have in my denominator 1 minus 4 times the square root of 36 is 6. I'm also going to go ahead and bring my numerator along for the ride. Okay, so I've got 1 minus 2 square roots of 6 over 1 minus 24. So then I have 1 minus 2 square roots of 6 over negative 23. So that's my final answer. Technically speaking, I want to get my negative out of the denominator. So if I was going to write this perfectly, I would write negative 1 plus 2 square roots of 6 over positive 23. Changing the signs on all of the terms through to get the negative up in the numerator. All right, so with that, that's a lot of information, right? We talked about adding, subtracting, and multiplying radicals with nth roots and also complex numbers, and then we spent a bunch of time on dividing radicals by either the easy way, quotient property, or the more challenging way with lots of different possibilities, rationalizing the denominator. Go ahead and try those couple of now you try problems for us to talk about in class.